So recalling the first principle of thermodynamics. Okay, what is it? Is heat minus work equal to the change in energy. Okay, all right. So let's say for a cycle, it's just to simplify, okay, to make it easier in understanding, but we don't have to do that assumption. So what is a cycle? A cycle, we say, could be like you start from one point and you end up at the same point. So for a cycle, what do you have? That the change, let's say in kinetic energy, you start the same velocity, you end up at the same velocity, is zero, no? If you start at one point, is zero, and if you start with the same internal energy, will also be zero. So for example, for a cycle, since the change of energy will be E0, then you have that Q will be equal to the work. Okay, so what is that equation implying? Okay, so that equation implies that above the equation implies that, let's say, this cycle, okay, I'm going to put process, doesn't need to be a cycle, is what? Is 100% efficient, no? You're just saying that you can transform all the heat into work, or you can transform all the work into heat. So it implies that the process is 100% efficient, and two, that the process occurs or can occur in both directions indefinitely, no? So you can transform all the heat into work, all the work into heat, and back and forth. This is not a direction. All right. So for the first one, for one, we already studied that. For one, okay, it was shown, and it's very easy the explanation, that a cycle / process can not be %100% efficient. Why? Anyone? What is the reason? This is important from the conceptual point of view. Okay, so basically the first law of thermodynamics, I put that already in the notes, implies what? Is that if we have here our cycle or process, so let's say creating work, all right? Or just say create, okay? You could do on the other direction. What does that imply? That if we do this figure, all the heat will be transformed into work, no? Okay, or if you want, you can do it vice versa. Or if you put the work inside, everything will become the heat. So now let me ask you again. Is this figure possible? What am I missing on that figure? the core reservoir. So basically we say that any cycle, any process, any engineering, any thermodynamic engine, any type of engine will always be operating between two temperature reservoirs, which make impossible for the efficiency to be 100%, no? Okay, so we already did it, and we already studied efficiency. So for one, it was shown that a cycle process cannot be 100% efficient because it must operate between two temperature reservoirs. So basically means that what we are missing here is the cold reservoir, no? Okay, so first principle of thermodynamics is doing that, all right? And for this, what do we say? The efficiency, if this is a power cycle, should be equal to what? Always efficiency, we say the general definition will be whatever you get out divided by whatever you put in, no? Okay, so if you want, what are you trying to create over here? Work. What are you putting? Heat, no? The total amount of work that you can generate would be Q hot minus Q cold. And what you're putting in is Q hot. I mean, we already did this. So this will give you that this is equal to 1 minus Q sub C over Q sub H. Okay. If you want, this will be Q sub H. This should be Q sub C. And let's say this will be a temperature Tc. And this will be a temperature T hot. So this could be equal to 1 over Tc over T hot. And I told you at that time that this equation is extremely important, okay? But you will see why in a few minutes. So basically the first, if you want, the efficiency of the first principle of thermodynamics is that it implies that everything is 100%. Really, we already studied it, which I do not like the order of the textbook. That's why I covered it before. Generally, I like to cover it here. Is basically resumed by, because we found all the different efficiencies. Remember, this is for a power cycle, but you can find efficiency for a refrigeration cycle or a heat pump, no? Okay? And the explanation would be the same in every single case, is that it needs to operate between two different temperature reservoirs. Okay, the second limitation is that the process occurs in both directions. And in this case, I'm going to give you an example that is very easy to understand, but it's not really 100% true from the thermodynamics point of view, okay? But for the explanation, it works good. So for example, if you want to transform liquid water into ice, it's not a problem because then you can recover the water from the ice, no? And you can go back and forth from the liquid water to the ice. So basically, this equality sign over here is kind of valid, okay? Now, what happens if you have a log of wood and you burn it? You're going to get ashes. Can you get the log of wood from the ashes? No, even though it's the same substance, no? Okay, so now what happens is that in that equation, really, the equal sign does not work in both directions. Once you burn your log, that's it, you got ashes, no? There's no way back. So it's a one direction process and there's no return, okay? So we need to define something which is going to help us to define when a process cycle can be bidirectional or when it's just going to be one direction. Okay? All right. So that new thing that we need to define is what is known as the entropy. Okay? Okay, so let's go ahead. Okay, so what we need to do now is to determine let's say a way to show that a process slash cycle can be. All right, so we just said the first case, let's say it's the water. You can become water, liquid water into ice, ice into liquid water. So that will be both directions. So in the Q, you see I do the sign, the equal sign with arrows. Let's say it's bidirectional. But in thermodynamics, they want to call that reversible. Okay, you can reverse it, which it makes sense. And the other one, let's say you will have just that. The example of the piece of wood, let's say, can just go in one direction. So let's say unidirectional. And this one is kind of funny because some books will call it non-reversible and some other ones unreversible. I think this one call it unreversible. Okay, so again, we need to try to define a way to show if something can be bidirectional, unidirectional, or what we'll be calling from now on reversible or unreversible. So the guy that did all this stuff, I mean, didn't do this stuff, really did the hard part. And then somebody else did really the part that is applicable, is Kernel, which is basically the 19th century, early 19th century. When was the beginning of the steam machine? No? Okay. So basically, let's go back to the equation. What did he realize? So basically, what he says that if you find the efficiency of, so basically what he did is this, which is everything, okay? Cycle process is the one that defined that you needed to have two temperature reservoirs. Okay, and let's say for a power cycle, okay? He did all these figures, so he had everything. But again, he didn't do the last step, okay? So what he says is that, okay, the efficiency of this, again, we know is equal to 1 minus Q cold over Q hot, or this will be equivalent to 1 minus T cold over T hot. Okay, so he wrote two things. So the first one is that he said the efficiency of a cycle or a process is independent of the substance. So basically, it doesn't matter if on the hot reservoir you have water, gas, oil. Really what matters is what is the difference between those two temperatures, no? So you see the efficiency is independent of the substance and only depends on the temperature difference. Okay? So one, first Kernel principle, first Kernel. I don't think it's very useful, but all right, so efficiency is independent of the, call it, working substance. Okay, and then the third one he said, and this is important one, he said the efficiency of a reversible cycle or process, but let's say cycle, is always higher than the efficiency of an unreversible cycle operating between the same temperature reservoirs. Okay, so basically say that the efficiency of an irreversible cycle will always be lower than the one of a reversible cycle. Okay, and if you want, this one will say substance 1 equal to the efficiency of substance 2, but that one is not that important. Okay, now that I'm looking at the equation, let me add something here to this equation here. So this is the general case, the general efficiency equation. All right, this is the maximum efficiency that you can get. So this will be for the reversible. So basically meaning if your process is reversible, then you can say that efficiency will be proportional to the 1 minus T cold over T hot, okay? If it is irreversible, you cannot use this equation, you need to use this one. You need to find what is the loss in heat and so on. But again, this is the important equation here. You're going to see why. Okay, so Carnot did all this stuff, which was really good, but the next step is really the important one. So the next guy is Clausius. And we're going to develop what is known the Clausius theorem, but I like to call it the Clausius inequality. I think it makes more sense. And that one is as well on the 19th century. Okay. So what did Clausius did? So Clausius, what he did is that from Carnot's work, so basically what did Carnot do? We just said is that if you have a cycle or process, that is operating between two temperature reservoirs, okay? So for the Carnot cycle, so this figure over here, you could represent it as what? What are we doing over here? We are operating between two different temperature reservoirs, no? Correct? So let's say we'll be here around T hot. And we could be operating here around T cold, no? All right. So now, how can we close this? So very easy. If it's a cycle, that means that you start from one point and you need to end up at the other, no? So if you want, you can do 1, 2, 3, 4. You can put the numbers any way you want. It doesn't matter. And let's say this will be the direction. So here you see this is a cycle operating between the two temperatures. Okay? All right. So Clausius was able to generalize it as follows. I think that was the very smart part, okay? So what Clausius did is that he said, okay, let me take a general cycle. Obviously, cycles are never going to be that pretty, no? So if you look at the figure of a cycle, it will look that way. If you have a motorcycle and you have a dyno to optimize it, and you start looking at the function of the cycle, it's always some type of ellipse circle. It's never going to be something like that, no? I don't know if you motorcycle that sometimes you can buy the dyno to actually check what would be the mixture between the gas and fuel, no? Okay, and you can depend on the temperature. So depending on the temperature of the surrounding, you can vary this stuff. But this will be the shape. It's not going to look this way. This is good. This will be the ideal case. This is a general case. But he did something very smart. He said, okay, all right, this is a general case, but let's say that I'm going to break this one, like if it was an integral, into multiple Carnot cycles. So this is a Carnot cycle. And he said, so for example, if you take this small enough, you can probably take this approximation to be like this, no? Let's say, all right, so let's say it will be here. I don't have too many colors, but let's say this would be the first cycle over here. This could be the second cycle. This could be the third cycle, and you could go like that to infinity. So I didn't do a very good job. So let's say this will be delta Q. This will be delta Q prime. You can do the other ones. So it will be the Q hot, actually. Q hot, delta Q hot prime. And here at the bottom, you will have delta Q cold, delta Q prime cold, and so on, so on. Okay? Sorry for the figure, I should have make it bigger. But you see what you have done. It's like when you do the integral of a function. Basically, what did you do? You break it into an infinite number of little rectangles, no? Yeah? And then obviously, the smaller the rectangles are, the closer your solution is going to be. Okay? Okay, so what he did is now he said, okay, we have this. So I know the efficiency for the first cycle. So it will be the delta QH. So this one first cycle. You have what? The efficiency will be equal to 1 minus delta Q sub C divided by delta Q sub H. And this will be equal to 1 minus TC and T hot. Okay? And I did not put it, but imagine that here on top you have a hot reservoir, and here at the bottom a cold reservoir, no? That they all those arrows go to the same reservoir. Okay. So once you have this equation, what can you do? You can cancel here the 1 and the minus 1. So you get what? That efficiency, but this is not the important part. You can write it as being equal to delta Q sub C over delta Q sub H will be equal to T sub cold over T sub H. Okay? Now, if we remember the sign convention for the book, sign convention for the book is heat going in is positive, heat coming out is negative. Okay? So the cold here is coming out, no? So actually this term should be negative. Okay? So we could rewrite this as minus delta Q sub C over delta Q sub H equal to Tc over Th. Or, and this is what is really smart that he did, you could write this as delta Q sub hot over Th plus delta Q sub cold over Tc would be equal to 0. Okay? Now, if we do the same thing for this second cycle, what are you gonna get? The same thing but with the primes. Okay, so if you follow the same procedure, exactly the same two-step, what are you gonna get? That delta Q sub prime H over T sub H plus delta Q sub prime C over T sub C will be equal to 0. All right, so now run out of space on this page. But let's just say over here, okay, following, so doing the same up to nth cycle. So basically, let's say you start from this one and you go all across all of them, okay? So what will you have? You have every time the same expression. So we'll have, in that case, we'll have delta Q sub hot over Th plus delta Q sub cold over T sub cold for the first cycle plus the prime let's say to the delta Q sub n this should be equal to 0. Okay, so you do all of this to the infinity. So if I simplify this notation, when you do all these ones, this should be like doing the summation. And you agree with me that the integral sign is the same as the summation. Okay? And we do the summation around this surface over here, around this cycle. So that's why I put the little circle over here. So if you do the summation of all the ratios, delta Q over T, they will be equal to 0. Okay, so why was what Clausius did so smart? Because what he did is that he had a general cycle, and now he say, okay, I'm going to replace it by an infinite number of ideal Carnot cycles. And if they are really ideal, they should be equal to 0, no? Okay, so basically what he's saying is that if this, when I do the summation, all of them are equal to 0, that means that it is the ideal case, and I can say that my cycle is reversible. Okay, does that make sense? Yeah, all right. I mean, I'm not going to ask you to do the derivation, but I hope you understand what I'm doing now, okay? And then he said, okay, I use the first Carnot principle. Let me use I use the Carnot principle. Let me now, what is the second Carnot principle? Is that so using second Carnot principle, which is what? The efficiency of an irreversible is lower than the efficiency of a reversible. So same as before, we just said before that the irreversible, the general expression will be 1 minus q sub c over q sub hot. Should be lower than 1 minus T sub cold over T sub hot. All right, we can cancel that. But again, what do we know? Q sub cold will be negative because it's coming out, no? Okay, so this one will stay negative. So what happens if you have a negative value when you have the bigger or smaller equality? It gets reversed, no? Or switched. So then you're gonna get that minus Q sub C over Q sub H should be higher than T sub C over T sub H. Okay. And now, I mean, the division is not that important. And now we move everything to the other side. What's going to happen? You're going to have Q sub C over T sub C. That should be what I'm keeping on that side would be the irreversible. I mean, that division doesn't matter, plus Q sub hot over T sub hot reversible. Okay, so now moving to the other side. So this should be lower than 0. Again, the division is not that important. We know that if the system is reversible, this ratio will be 0. So basically from here, what he was able to conclude is that for this one, I changed the notation. The ratio delta Q over T going around the circle should be lower than 0. And this is cycle is unreversible. Or irreversible, I don't know how they call it. How do we call it here? Unreversible?
Unreversible.
Okay, so I think actually the book call it irreversible, and some other texts will call it non-reversible. So I don't know. Doesn't matter, okay? Okay, so what is Clausius inequality? Clausius inequality, the guy was extremely smart. So finally, what he says is that, okay, if the ratio delta Q over T is equal to 0, we can say that our cycle is reversible. And if it is lower than 0, it's irreversible, but I think I started using unreversible, so let's start unreversible. Okay, so what was the second deficiency that we had from the first principle of thermodynamics? One was that the process could not be 100% efficient. The second one is that we needed to be able to find if the process was bidirectional or unidirectional, no? So is that going to give us a tool? Yes, okay. But now let me ask you something. Try to imagine physically, what does the ratio of the temperature of the heat divided by the temperature means? Pretty strange quantity, no? Okay. Personally, I have no idea. Okay, wait, no idea. So basically, what Clausius did is that he defined this ratio as a new quantity that we're going to study now, which is the entropy. Okay. So Clausius defined the ratio delta Q over T as the entropy. Okay, so let's say entropy will be delta S delta Q delta T is equal to S2 minus S1. And this will be S is entropy. All right. And what will be the units? That's not difficult. Joules per Kelvin or BTUs Rankine. Okay, so let me finish a little bit the lecture for today, and then I'll try to make this a bit more clear, okay? All right, so Kelvin define the concept of increasing entropy of the universe. Okay, so let's put it this way. If we accept that nothing is perfect, so what does that mean? Is that once we have many times, if you want, we burn a log and we get ashes, we cannot go back, no? So what does that mean? That if you cannot recover the energy you use, you wasted some energy, okay? Every time you waste some energy, what's gonna happen? You won't be able to get 0 over here, no? Okay? So what he says is that every time we don't have a process that is reversible, what we do is that we put entropy, the ratio delta Q over T, into the surrounding of the universe. Okay? So as we have many cycles that happen all the time, what happens is that the entropy of the universe keep increasing every single time, no? Okay? So now you're gonna get philosophical. When do they say it's the end of the world? When we'll have no more energy to use, no? No more energy available to use, and in that case, what will happen? We'll have an infinite entropy. I know some of you love that definition of entropy. What is entropy? Chaos, no? So chaos, that's it. That will be the end of the world, no? Okay, you can even do philosophy, all right? With entropy, okay? So basically he just defined the increase in entropy, and he's just basing what I just told you. Nothing is perfect, so the entropy of the universe is going to keep increasing, okay? So what he defined here is change of the entropy of the universe will be equal to the delta Q over T, all right? That will happen of our process with the surrounding plus whatever can happen during our process or cycle plus delta sub S of the process. Okay, and here, be careful with the term delta Q over T, because sometimes I've seen that it creates some issues. So this is our process or cycle. Since I put process here, let me put process. All right, and let's recall the sign convention for this. So let's say to make a difference, let's say this is QH and this is Q cold, doesn't matter. Okay, let's say this would be T reference. So let's say this is operating at some T reference temperature. Okay, so now this is based a little bit on understanding. So if we say entropy is a measure of how really you use the energy, this is the good definition I like, but let's say, since that definition you like, it's a measure of chaos, no? Okay, so what happens if you put heat into this process? Is it going to increase or decrease the entropy? I mean, if you put heat into here, what's going to happen to the molecules? They're going to heat more each other, no? So more disorder will be to increase the entropy. So this will increase entropy, meaning that this term will be positive. Okay? Now, what will happen if you remove, let's say, from this room heat? What will be the opposite? It will decrease entropy, and that term will be negative.
What are the subscripts on the T?
Oh, T reference, doesn't matter, just T. Because here, what happened, I didn't mention, you could take as a reference value the value of the hot reservoir or the value of the cold reservoir, no? Or you could take any temperature, but as long as it's the same temperature for both. Okay, Janet will be the temperature of the surrounding. That's what you will take. All right, and this will be page, I think I forgot to keep track of the 76. Okay, so let's see, we have time to do an example. Be good if I can finish, because it will help for the understanding. All right, so in our example, let's say we have a tank of water that is divided into two compartments, and there is a valve in the middle. Okay? On one side, we have cold water. Let me use the values that I have here so that you don't have to do the calculation. We'll go a bit faster. So we know that T cold will be 15 degrees Celsius. And then on the other side, you have hot water. And let's say that one will be at 80 degrees Celsius. You have an amount of hot water equivalent to 4 kilograms. And let's say an amount of cold water equivalent at 3 kilograms. And the question here is assuming a constant specific heat C sub V equal to 1. To make things easy, determine VA, average temperature of mixture, and B, if process is reversible or not. Okay, it's faster than to have to write unreversible or irreversible. Okay, so here, before we start, let's start thinking a little bit about it. So if we open the valve, you agree that we're gonna get warm water, no? So we need to find out what will be the temperature. If we have the same amount of mass of hot and cold water, you just do the average, no? But it's not exactly the same mass, so we need to do something a bit different. Now, can you get, once you have the mixture of water, can you get again hot water and cold water without doing anything? Probably no. So you see, so this process should be what? Should be irreversible or non-reversible, no? So let's see how we can prove that. All right? Okay, so for part A, we use again the first principle of thermodynamics, which will be what? Q minus work. In this case, do we have kinetic energy? No. Do we have potential energy? No. But you agree that the hot water will have some internal energy and the cold water will have some internal energy. So it should be delta U. Okay? So again, everything is from the figure. Do we have any heat being added or removed? No. Do we have any work? No. So basically what we have over here is that the change in internal energy is equal to 0. Okay, and some people, you get stuck over here. All right, so let's look at the figure here. What's going to happen? You're going to have change of let's say, internal energy. Let's start by the hot one, okay? Let's say you will have hot when it will become to a mixture, plus change of internal energy now of the cold to the mixture should be equal to 0, no? So basically, I'm just saying there's a change of energy, 1 for the hot water, 1 for the cold water. Now, does the substance water remain in the same state? Both liquids. So can we do the ideal substance assumption? Okay, so the ideal substance assumption will be what? That delta U is proportional to mCV dt, no? Okay, so I could say this will be m hot CV. And now what will you have? T mixture minus T hot. Yeah? Okay, final minus initial, no? U2 minus U1. Plus, now we do the same thing for the cold. M cold, C sub V, T mixture minus T cold should be equal to 0. So over here, if we do the algebra, you will see that this will cancel and we'll end up with what? Temperature of the mixture should be equal to what? So will be M hot T hot plus M cold T cold. Okay, I'm keeping the middle step just to make sure we finish or try to finish. And then at the bottom should be T cold or T hot, M hot plus M cold. Okay, so if we do the numerical application, we're gonna get the temperature of the mixture should be what? 4 times 80 plus 3 times 15.
We use absolute temperature.
In this case, you can use these ones. You can move it, but what's gonna happen? You will have 273 plus 273. What matters only the difference, no? Yeah, but it would be, if you want, you can move everything to the absolute temperatures, okay? And then this would be what? 4 plus 3. Basically, you can factor out by the 273, no? So it doesn't change anything.
Even though you're multiplying?
Yes, exactly, because it's multiplying, because you can factor it out. Basically, these two here will be added by the same term, no?
But isn't it different because the masses are different?
Okay, so let's do it if you want. Okay, let's see what will happen here. All right, so again, here you can use the absolute, or the absolute is because basically you end up adding the same term to both of them, okay? But I mean, it was a good question. Instead of doing the whole mathematics, we just check very quick. All right, so that was part A. Now, part B is obviously the interesting one. Okay, so I'm gonna try not to rush it. If we finish it, good. If we don't finish it, okay, bad luck. So we have the first principle of thermodynamics gonna give us heat minus work will be equal to the change in internal energy, okay? Same as before. But now what do we know? That the new quantity entropy is equal to basically delta Q over T. So if you think about this is first principle, this is the definition for entropy. Okay? So, and let's say here that delta Q is more or less equal to Q, all right? So if we combine the two equations, so combining both equations, what do we get? We're gonna get that Q minus work equal to change in internal energy. You can rewrite it as what? Delta T delta S. You agree? Okay, from this one you can say then that delta Q will be equal to T delta S, no? Yeah? Delta Q, that is Q, will be T times delta S minus work equal to the change in internal energy. Okay, what is the definition of work? Work, we say, Johnny, would be the work done by the pressure. So you see we have PDV. So really, if you want, this will be, I know you know with the integration, so let's say partial of work, virtual work, PDV. All right, so all this stuff is going to become a little more complicated here. Just the notation, okay? Just the notation. T delta S minus PDV will be equal to the change in energy. Oh, it's good. This problem is going to help us to simplify this pretty quick. Good. So in this problem, what do we have at the end? This is our system, no? Yeah? What can you say about the system? That the volume is constant. Correct? So if the volume is constant, what does that mean? There's no change in volume, so this term will be 0. So from here we can say now that T delta S will be equal to the change in internal energy. Okay? So now we can say that the change in entropy, let me write one thing here. Before, what do we say? Since the water is not changing state, we can say this should be equal to M CV, let's say dt delta T. What do we use here? Delta T, no? Yeah, for analysis substance. So we can say that the change in entropy should be proportional to M C sub V delta T over T. So now if we integrate both sides, what do we have? Change in entropy will become S2 minus S1, should be equal to integral of mCv delta T over T, which will give us that S2 minus S1 should be equal to what? mCv, if this is constant. What is the integral of dt over t? Will be log of T2 over T1, no? Really should be log of T2 minus T1, but you know that log of A over B is equal to log of A minus log of B. All right, so this is what we have. Okay, so in our case, what we're gonna have? For the present problem, what do we have? We're gonna have, so our total delta S will be equal to the S sub 2 minus S sub 1 hot mixture plus the S sub 2 minus S sub 1 called mixture. Okay, so let's start thinking. Okay, write this down and then we think a little bit about it. Let's write the following line and then we think about it. So this will give you what? M hot CV log using this expression of what? What should be T2? Should be the Tm, no, the average temperature, divided by T hot plus M cold CV log of T sub M over T of cold. Okay, so before we go and do the calculation, let's just think for a second about it, okay? So basically here we have two waters, hot water and cold water. And we're gonna get warm water, okay, at 52.14 degrees, all right? So what's gonna happen to the entropy of the hot water? Is it going to increase or decrease? It should decrease, no? Now, what should happen to the entropy of the cold water? It should increase, okay? So let's see what happens once we apply the numbers here. So if we rewrite this here, this equation here, we do the numerical application. So let's say here, numerical application. We're gonna have that delta S should be equal to what? So M hot was 4, CV is 1. Here, yes, we need to move to the absolute temperatures. So it will be 52.14 plus 273 divided by 80 plus 273. Hopefully this value will be negative, no? We said the hot water is going to lose entropy. Plus 3 times 1 times log of 52.14 plus 273 divided by 15 plus 273. Okay, so as you do the calculations, I also have the values for this for once. So, but please do it anyway. So basically, what do you see over here? Hot water lost entropy. Okay, cold water is gaining entropy, no? All right, and if you do the summation of both of them, you get about 0.035, and you see that this term here is positive because the summation of both of them should always be positive or equal to 0 because of Kelvin principle of increasing entropy of the universe. If you get a negative value here, you have done something wrong, no? Okay, this value is either 0 or positive. So that means that this one is higher than 0. So basically you conclude that this cycle is irreversible, or we're just going to say non-reversible. Or as your textbooks say, irreversible. All right, so for today I'm going to stop over here, but again, there's a little difference in notation between what I do on the class notes and the textbook, and I will address it next class. So to finish, since we have 4 minutes, if I want you to remember a definition for entropy is the following one. Entropy is a measure of how well you use the energy that you have available, okay? So if you use it wisely, what does that mean? That you're gonna have your change of entropy to be equal to 0, no? If you don't use it wisely, it will not be equal to 0, and the higher the entropy, obviously, the less efficiently you're using the energy that you have available. All right, so, okay, I'm good. All right, so we stop over here, and next time we do more examples, and I think I forgot to define what is the second principle of thermodynamics, even though we did it. It's just when you combine the first principle and the second one is what is known as the second principle of thermodynamics. So again, we do that next time. So this should be here, page 79. Thank you so much. Have a good day, guys.